Thank you very much. Thank you very much for the organization, for the conference, and for the whole trimester. I think I'm a lot of fun here, and I will be staying here a lot. So for people who are staying, I'm around. For people who are coming and going, I'm around. And for those who are not coming back, it's really sad. The conference has been amazing. So somehow it's an honor to be the last speaker, but somehow also a responsibility, because I imagine all of you are tired. So I try to do like with kids, there are a lot of drawings. Not here. So I'm going to discuss about the excursion decomposition. So I will say what this, but this is based in joint work with a lot of people. So Tomás Alcalde was here last week. He's in Vienna. Juhan Aru, Titus Lupu, Lucas Chow, Frederick, who was also here, Benjamin Werner. And I was wondering whether to put Ellen, she's in some hidden part, but the real part, and I will discuss about the imaginary ones. So what I'm going to talk about, so mostly the first thing I will do is describe the excursion decomposition, and then I will discuss it in 4 models. So fundamentally will be random walk, the first one, the Ising model, Gaussian free field, and XOR-Ising. Both, like all of them, have a excursion decomposition, and we are going to discuss the features, how to build them in each of them. So let's start with what is the excursion decomposition, and here is the first drawing. So I did a simple random walk, and I colored in as many colors as it allowed me Mathematica, no, it's MATLAB, to just mark. On what I'm marking the points where the GFF itself has just one value. So these are the connected components. So the Brownian motion itself has one value. So these are negative. This is the connected component where it is negative. Here it's where it's positive. And here, as you can see, when you hit 0, you have finitely many or infinitely many according to whether you are a Brownian motion or a random walk. And so, of course, that means that the walk itself can be written as a sum, as an infinite sum of measures, which is in the part where they are either positive or negative, times a sign. And what Ito taught us, and what is somehow clear to see in the random walk case, is that these signs are i.i.d. Yeah, so the i.i.d. Bernoulli 1/2. So this is what I will mean by excursion decomposition. To be more precise, phi has an excursion decomposition if it can be written as an infinite or finite sum of a measure times signs, but I want something else. So first I want that the measures have a connected support. So I cannot say like these two are the same, they're connected support, and furthermore the supports are pairwise disjoint. So this is true for the Brownian motion, because between 2 excursions there are infinitely many small excursions. And this is true for random walk because the measure is not supported on the points where it hits 0. So in both cases this goes on. And furthermore, I want sigma k to be i.i.d. Bernoulli 1/2. So they are independent, and they are also independent of the measures mu themselves.
So yes. I'm a bit confused. So phi is the measure?
Phi is,
you mean your right
phi is the field. And
then what do you mean by measure on the right side?
So what do I mean by measuring there?
On the right side.
So there is a measure on the field. So here the measure was thinking about is this measure. So when I integrate against the Brownian motion, I get a negative value here. So it's integrating against the measure whose Proudhon-Nikodym derivative with respect to Lebesgue is the value of the Brownian motion itself. So that will give you a measure. It gives you a value at each point. So what we will see are things that become distributions afterwards. So that's why I'm putting measures. So mostly we're going to work in dimension 2, and I will have positive measures on top of things. And they will be either positive or either negative. Okay? So
in the Brownian motion case, what do you mean by, so the mu k is an excursion measure or something?
Yeah, so no, mu k is simpler. It's just the values of the Brownian motion restricted to the excursion. So it's 0 everywhere?
Yes, it's a function.
Yes,
In this case,
yes.
it's a function.
Yeah, so it's simpler. It's not
So it's a random measure. It's not a law. It's a random measure.
Yes, it's a random measure. It's not a probability measure. I'm thinking. So, so why excursion decomposition interesting? Is because they allow us to transform the problem of looking at correlation functions as a problem of connectivity. So essentially, if I want to see the signs of my function at 2 points, then this can be read as x and y being in the same cluster. So if x and y in the same cluster, of course they have the same sign because the cluster is multiplied. And if they're in different clusters, then because the signs are i.i.d, they mean out. So this is the great story of excursion decompositions. So this slide we're going to see it for each model, and it's going to discuss about the measurability of excursion decompositions. So in the case of Brownian motion or random walk, the support of the measure is a function of the field itself. And what is the support of the measures? Here are just intervals. So this interval, I can just, if I see the Brownian motion, I see exactly which are the excursions. This looks at this point quite obvious, but we will see that this is not always the case. However, the measures themselves, meaning the values of the Brownian motion inside this interval, is not a function of the support. I just know the length. And in fact, we know essentially what is the line. We know what is missing. So it's just an excursion. It's just an excursion process, or going from this length, meaning it's just a random walk or a Brownian motion, a bridge going from here to here, conditioned to keep the same sign. Yes. So all of these things were understood by early in stochastic calculus. However, they appear again in statistical physics everywhere. So then the model that one needs to see, and I think most of you are used to seeing this excursion decomposition, even though it's not called like that, is in I.i.d model.
Could you go back to the definition of excursion?
Yes.
It's just very...
Yes. So what I'm not being clear here is how the sum is going to be taken. That's a little bit subtle because we will have infinite everywhere appearing. So if one doesn't order things well, things will get messy. But I will not get that much into the order of summations.
So it's important for you that the sigmas are independent of mu, right?
Yes.
That's part of the definition.
That's part of the definition. Yeah. So this is what I will understand as excursion decomposition, because if not, I will not be able to have this connection probability.
Thank you.
Perfect. So now how do I build I.i.d model? So one could say, okay, given that what I did for random walk, essentially excursions are going to be just connected components of things that have the same sign. Yes? But this will not give independent signs. Essentially because one cluster will be adjacent to a positive cluster will be adjacent to a negative cluster. Then clusters are not independent. So then this is when the fourth FK model appeared. So essentially what you do is the following. So you will start with an I.i.d model, let's say, and we will build a line. So here I'm just looking at the red. So we will build a line between each vertex that are neighbors and they have the same sign for I.i.d. And then somehow we will randomly select which one of these we keep with probability. I have to remember it's 1 minus exponential to the minus 2 beta. But let's say you toss an intelligent coin in every edge and you will erase it. So this will create a photo clustering clusters. So you can see it here. So essentially here, this works for any temperature, for any graph of the I.i.d model, but I'm usually going to concentrate on two-dimensional things, at least in the continuum, where I can do things. So here I sampled an I.i.d model at the critical temperature, just because it's more beautiful to look at than really cold or really warm. And as you can see here, there are black things and white things. And then I broke them into clusters, following the laws that it has to be. And you see different colors. So the colors are now the connected components of the FK model that is left. And in this case, the statement is that in fact, this is an excursion decomposition, meaning that if to each one of these clusters I toss an independent coin, yes, and then I put value either +1 or -1 because my measure is a uniform, then the law that I will have is that of the I.i.d model. Okay. This is quite fun because somehow it allows you to resample the I.i.d model, no? Because I could toss again the coins. So
the breaking was random or not?
the breaking is random.
So each edge
Each edge is independent.
Independent.
Independent at random. Each edge.
I was would say independent.
Yes, each edge is independent at random, but with a probability depending on beta. That somehow I think will. Why is that one? Somehow it can be explained by the GFF. It's a really complicated way of explaining a simple computation. But can be. So this was introduced by Fortuyn and Castellet, and develops after what's called Edwards-Sokal coupling. And there are many uses, but I'm not an expert on the Ising model, especially on the discrete side. So I have been trying to ask ChatGPT quite a lot to see what are the most important. So I felt like a bad student. But at least one that I have just used is mentioned one algorithm to sample Ising model. If you come back, now if you read those coins, then you get another Ising model. So you get a natural natural dynamic on Ising model that somehow resamples everything at once. And that's nice to sample things, because Glauber, you just sampling one by one, it takes infinite amount of time if the temperature is not too cold. If it's not too warm, sorry. So then there are some stories about proving Russo-Simon-Welch for FK, which allows you to somehow decouple quite well Ising, and that gives estimates on mixing times of things like that. There is the sharpness of phase transition of the Ising model that was proven also using FK representation, and in dimension 1 there is this continuity of long-range percolation, which was proven. So there are two proofs using FK representation. So it's usually, why did I have so many problems with ChatGPT is that not all of these proofs were only done using FK representation, but somehow it's the simplest way, and it's the modern way in many senses, in particular because it allows you to take things that you know how to do for percolation, do small changes, and sometimes it makes you work for Ising, which is surprising in a way.
So do you have a continuum?
Thank you. So what happens with the continuum counterpart? I was not prepared for this. So FK clusters, so meaning the clusters of the excursion clusters, are converging to CLE16/3 clusters. So this was work by Barney and Smirnov in a paper which many suffered to read at the beginning. So Garvan and Wu rewrote the proof in a much simpler way. And as Leonie was discussing, one has convergence of both the magnetization field. So the first one is the magnetization field. I put delta to the 1/8. It could also be read as, so it's, it's a 15/8 or 1/8 according to which is the right observable you are seeing. But after a right normalization, things are converging correctly. So there should be -1/8. But also the measures on the measures mu k of FK cluster are converging at the same rate. And so this first one so both of these are the work of Garvan, Camille, and Newman, but they centrally use, at least in one construction, this work of Chekhov, Ongler, which gives explicit description of the endpoint correlation function, and the only thing what they need to prove is that they have exponential moments, which they do using some GHAs inequality. So you have exponential moments, so essentially the first part is easy after a really hard work of getting the endpoint correlation functions. But at the point, Camille, Garvin, and Newman were not that happy with that, because the paper of Chekhov, and Ongler is hard. And because it's hard and it hasn't been published, you are a little bit scared of citing them. So in the original paper, Camille, Garvin, and Newman, they had this idea of saying, okay, let's do another construction. So we already know that this thing works, and what they say is like, okay, we know the FK representation is converging in a way, and so what we need to show are that the measures on top of the clusters, are they converging by themselves? And they show that in fact they are converging to a measure which is the Minkowski content measure of the right dimension. It has to come with the 1/8, and that gives them direct excursion decomposition. Just a little bit by what China asked, and there's something, what happens with the CLE 3, it's an interesting story. This is not an excursion decomposition. I'm not going to talk about it, but this is my trailer for an upcoming paper. So stay connected. So just what are the measurability properties? So in this case, the support of the measure is not measurable with respect to the field itself. This is clear in the discrete. It's less clear on the continuum, and this will also come in the upcoming paper. I mean, there is randomness. You cannot get out of looking at the field. You cannot get what are the right ways to decompose it. However,
What is the psi?
yeah, the psi is the continuum limit.
The magnetization field.
Yes, the magnetization field. However, the measure now, the measure now is a function of the shape itself, which was not the case for the random walk. We just have an interval, but now there is some geometry that appear, and somehow one has this measurability. Okay. So this is what I wanted to discuss about the Ising model. So as you see that there are some fun things about here. So now we come back to one of my biggest friends, which is the GFF. So what does happen in the GFF story? The GFF story, so if you have never seen a GFF, that's a GFF, it's pretty spiky. Yes, it's I'm working in the continuum on the discrete. And so it's a function that we all know, but I like to think about as being proportional to the Dirichlet energy. And I have this divided by 4 pi, so which was the big discussion in Nathaniel's talk. My GFF correlate logarithmically, just because I don't have a constant in front. It just makes everything simpler. So, of course, we know that the GFF is the generalization of Brownian motion when time is changed by a metric space or something. Yes. So, Brownian motion, we knew that to look for an excursion decomposition, we have to look at the clusters of the same sign. So this is what I did. I took exactly the same simulations you can realize directly by the eye, and I look at which points were positive, which points were negative, and I just plotted it here. And you can say this should be the excursion decomposition. However, if you really do have a good eye for excursion decomposition, you realize that this cannot be the case. And let me try to convince you why this cannot be the case. So note that, look at this, try to follow this boundary. We are going to discuss about these boundaries afterwards. But these boundaries, they tend to be really like the boundaries of the clusters of signs. It doesn't look like they are broken. However, these are really separating 2 clusters of signs. So it is impossible to get independence of signs out of this story. So it should not be possible. So this cannot be like in the case of Brownian motion. So what has to be done? We have to do as in the case of Ising. We have to break apart clusters so we get independence. And how do we do this? So this is an idea of Titus Lupu, which is as following. So to each edge of your field, you will add a Brownian bridge with a certain right temperature. So the length. Going from each vertex to each other, so Tomás Alcalde did the simulation. So the idea is like you have 2 points here, and then as you see, you follow the random walk up to them. Why does one do this? Why, for example, I don't put another process like Hausdorff? Well, the reason is that this one gives you the Markov property even if you stop at edges. So we are going to use strongly the Markov property of this thing. So you can stop mid-edge. So you can have a set of edges mid-cut, and then the law outside will be that of a Gaussian free field plus the harmonic function generated by it. So it's quite cool. And now, what we can do as excursion decomposition is not looking at places where I change signs, it's just looking at the points where I hit 0. So a connected component now is just really the connecting component on the metric space given by changing each edge of the graph by a copy of 0, 1. And then one gets an excursion, and for this excursion, in fact, what has the excursion decomposition. So just to summarize, for the case of what I call metric graph now, which is this metric space, I have excursion decomposition, which is measurable to a set. And how does one prove that this is the right excursion decomposition? Is because, well, if I take one point and I look at the excursion associated to that point, the law outside of it, well, it is that of a zero boundary GFF in a weird domain, but this has a reflection property. So now I can, because all the boundary conditions are 0, I can put plus or minus, so the signs outside have to be independent of what I have seen. So this was introduced by Titus Lupu to inverse Legend's isomorphism. That's essentially the trick, separating things and then saying that they were independent. However, they can also be extended to the continuum. So there's a work of Ken and Werner making convergence of certain observables, and we give a whole description of this object and a whole continuous construction with Titus Lupu and Juhan Aru. Furthermore, it has the same property as that of the Ising model in the following sense. So if I know one cluster of the decomposition, I can directly construct the measure living on top of it. But it's also a Minkowski content, but now the gauge is weird. And why? It's because this is a two-dimensional. The support is two-dimensional, but has zero Lebesgue measure. So in fact, there is like a square root of log R object that appears, and that one should think about it in the discrete case as being the typical value of one point of the GFF conditioned to be positive. That will also give you a square root of log. And furthermore, one can exactly describe the law, one can exactly construct these excursions out of the loop subcluster. So this is even true not only on the continuum, but also in the discrete. Also on the metric. So the cool thing about the discrete / metric in this case is that this can be worked for any type of graph. However, we can only do the excursion decomposition in dimension 2 in the continuum. And there are some kind of nice stories that this is a whole paper of Wendeling trying to say what this is going to be when we take the higher dimension and why somehow dimension 6 becomes critical for this story. So this is an image of the loop sub of intensity 1/2. So either you know what it is, and if not, just think about it as every connected component you see here is a connected component of signs of my GFF, my metric GFF. So just, again, the same picture as before. So in this case, and this is a little bit tricky, so I want to keep it simple in this slide, but in this case, the support of mu k is a function of phi as long as we are in the metric or the continuum GFF. In the discrete, no, because we had to add this breaking point. Furthermore, mu is a function of the support. So this time everything is positive somehow, everything is measurable. If I have the support, I can get mu. And this is true only in the continuum, two-dimensional continuum. This is not true on the discrete, because there is some randomness I have to put, and this is not true on the discrete either. Okay, so at this point, I would want to comment about the relationship between this one and the excursion decomposition for Ising. Essentially, Ising model is just a GFF condition to take norm equal to 1 at every point. In dimension 1, take values equal either square root beta or minus square root beta. And the excursion, one can use the excursion decomposition of GFF to show the excursion decomposition of Ising. Meaning that Ising model also has the property that if I put Brownian bridges between the edges, I will still have the Markov property for Ising model. So essentially both Ising model and the GFF, which is essentially a generalization of random walk, have their excursion decomposition due to the Markov property according to something that one can put on the edges. Let me tell you something about the proofs of this story. So how does one get to prove something like this? So there are two ways of proving scaling limits. So either, well, there can be a mix between both. Let's say any proof of scaling limit is a convex combination of two extremal ideas. Either you really understand well the discrete system, like in the case of Camilla, Garvan, and Newman, where they show the excursion decomposition of the Ising model. If you understand it really, really well, then somehow you can guess what's going to go on the continuum and just push the scaling limit. And the second idea is to really understand well the continuum object. And when you really, really understand well the continuum object, then you just somehow prove tightness in the discrete side, and you say, it can only converge to this object here. And this is going to be the idea of the excursion decomposition for the GFF. So we are going to build them by hand on the continuum, and then we are going to, then one can say, okay, this is converging. That's another work. So for this, we need to be able to understand what are two important Markovian sets for the field. So one is the two-value set. So as you know, in dimension 2, the two-value set does not have values. However, I would want to build the following object. So I would want to say, I would want to build a set such that a point belongs to the set if and only if there is a path that is connecting it to the boundary of the domain where I think that the GFF takes value 0, where the GFF takes value between minus a and b. Okay. This is a priori not well defined. However, I want to convince you of the following. This set, if it exists, it doesn't. It should be Markovian. Okay? So it should induce a Markov decomposition on the field, meaning I can write the Gaussian field as the sum of two things. Pi, so something that's a harmonic function outside the set, plus some GFFs that are independent. So let me put it better. Imagine that this is a set. Okay? So the black parts are the set. Okay, so inside each white part, I will have a harmonic function, in this case constant, which will be equal to either minus lambda or lambda. And I want to claim that this is what happens when you do this, when you have a continuous function, because if you have one side that was minus lambda, and then was cut by other that is lambda, I can still continue entering my domain. Yes, by intermediate value theorem. So it should just give me either minus lambda or plus lambda. And because it was Markovian, then inside each of these white parts, I just have copies of I have just independent GFFs with 0 boundary condition, or if you want, with minus lambda boundary conditions, if you want to think of it. So you have independent GFF here with 0 boundary condition plus either minus lambda or plus lambda. So that's what I understand as a two-value set. It's a Markovian set, meaning a set that induces a Markovian decomposition of the field, such that the harmonic function it induces takes just two values, minus lambda and lambda, and somehow something that looks innocent, there is nothing living on top of the black thing. There is no more information. I can really recover my field as the sum of these two objects. And what we proved with Juhan and Vendelin, the start of my thesis, is that in fact these sets do exist as long as there is enough space for the GFF, which is natural. The GFF just fluctuates a lot. So if you want to work, you have to be careful not to ask it to have too small of a differences. But then there is explicit value, there is explicit value, which is for my normalization pi, justifying the normalization, I think, that such that if the difference between both of them is bigger than pi, then these sets exist and they are unique. Furthermore, they are measurable with respect to the field. So you give me all of these awful things and I can find yourself the curve. I will take the time, but I know how to do it. It's fun when the height is not as big, then they do not exist. So this is the second one we are going to see. So the set is the blue part, and this is a simulation by David Wilson. So here so in this case, so this is a really special case and will play a special role in the decomposition. It's a minus 2 lambda 2 lambda, so it's a minus pi pi. Then this is equal in law to a CLE4. And this is the first two-value set introduced, in fact. Well, the second important two-value set introduced, they say, okay, this is a CLE4. If you take a CLE4 and then you put plus minus 2 lambda inside of each of these holes with the probability i.i.d in each one of them, and then you add to these ones independent GFFs inside of each one of these holes, then the law of all of this weird sum is exactly that of the GFF. So this thing was proved by Miller and Sheffield. Somehow they announced it, and then we proved it with Juhan and Vendelin. And you get something more. So you get that conditionally on the geometry, that a minus 2 lambda exists, but it has the law of a CLE4, and that conditionally on the geometry of a minus 2 lambda, the harmonic function you are seeing is just i.i.d. So this is what we were expecting to build an excursion decomposition. It doesn't depend on geometry. Furthermore, these are the only values of a and b that do this. There are no other ones that satisfy this condition. So okay, so this is a good direction to build our excursion decomposition. We wanted to get i.i.d. signs somewhere. It naturally appears here. And now we have to build the other set. So we have exiting minus av. It's natural to want to exit minus a infinity. So these are the first passage sets, and they have to be thought in the same way, meaning a point belongs to my first passage set if there is a path connecting it to the boundary, where the GFF itself is always bigger than minus a. Okay, so yeah, so I did like this. So here I have a sampling, a minus lambda. So it's a minus pi over 2. So now what happens? So I am exploring until I hit level a. Yes, let's say until I hit level lambda. Okay, when I hit this level, like everyone here in the middle is just looking at boundary conditions equal to lambda. This is quite natural. So one kind of has, minus lambda. I'm hitting until I hit level lambda. Everyone here is looking at boundary conditions minus lambda. And I said that this field induces a Markovian decomposition, meaning that the GFF inside the GFF can be written as something which is on the white part is a harmonic function plus an independent GFF on the domain, and on the black part maybe there is something. Okay, so look that now I added lambda. So now on the white parts I have boundary condition 0. Okay, so it feels like this guy wants to die, and we will see that it doesn't, because there has to be we have to keep the mass. The expected values of both sides have to be the same. So okay, so this creates. So this allows us to define with Juhan and Titus what we call the first-passage sets, and essentially what we say is that for each A there is a unique first-passage set A minus A, such that it has a Markovian decomposition. Okay, so the first one tells you this is Markovian. The most important is the second one. It's telling you that phi A plus A is a positive measure supported in A, meaning, which is quite natural. If you were doing it in the metric graph and then we walk until we hit level A, we are just seeing things that are bigger than minus A. So if I add A, I'm just seeing things that are positive. So it is a positive measure. It is not obvious to see it's not trivial, but it is also non-trivial. So here I'm showing another key player. So this is A minus 2 lambda, meaning I start at 0 and I get all the way up to minus 2 lambda. Or how we will want to think about it, I start at 2 lambda and I walk all the way until I hit level 0. And in this case, I'm getting a positive measure and I have 0 boundary condition. So now let me tell you how does one construct. So now we have all the tools to construct an excursion decomposition for the Gaussian free field. So the idea is the following. We start.
So, yes, so that I understand. So what you call the measure, the positive measure,
yes.
Is a GFF condition with these boundary conditions, condition to be positive? Is that
no. So what I call the positive measure is the following. So
what do you mean by positive measure?
So imagine that you have the. So let me work on the metric and I will go to the continuum afterwards. So in the metric graph, you start with, imagine that you have a GFF with boundary condition 2 lambda, so it's pi. Okay, and now you are going to go through the continuum until you hit 0. So essentially you will have a random set that you have built in your, which are your explore set. And then on top of the set you are always positive. Yes, I think of this as a measure. So I think of positive functions as measures.
No, but it has a law, no?
Yes,
it's
so
not deterministically in the.
Yes, so in this case,
yes,
which would
what is the law of that? And it will be a GFF condition to be positive.
Yes, so inside, exactly as you say, like inside of the explore domain you have done, you'll have boundaries where you know that you are 0, yes. And then inside somehow you have a metric graph GFF condition that everywhere you are positive. So it's like an excursion measure.
Okay.
Yes.
So that's in the metric graph.
That's in the metric graph. So when you go to the continuum, this measure itself, so the set itself becomes really small in the sense that it has Lebesgue measure 0. However, it has Hausdorff dimension 2. So now it's a really thin set, and what one can show is that this measure becomes deterministic according to the geometry. And this measure is this Minkowski content measure of R square.
Thank you.
So just because somehow I thought a lot about these things, in a way this would be the typical value of a point from the metrics point of view. So if you take up this random weird set, you take a point, you take the expected value, it should be this. What we are seeing.
Thank you.
Okay. So now, how does one construct the excursion decomposition? We need to get the i.i.d. signs. So we start with a minus 2 lambda 2 lambda. So maybe I will use this notation afterwards. They told me they were really heavy. Okay. So here I start with the GFF, and the first thing I will sample is A minus 2 lambda, meaning I get two options. I either get minus 2 lambda as boundary condition, or I get 2 lambda as boundary condition. Both of them work. And then I have to say what I'm going to do inside each one of them. So inside the minus 2 lambda, I want to come back to 0. How do I come back to 0? So now, so here I have the GFF minus 2 lambda, and for this one I just will sample a 2 lambda, and I will get a negative measure here. And I will come back to a GFF, to a normal GFF. And in these ones, I will, so this one makes me come back to 0, and in this one, of course, I have a GFF plus 2 lambda, so I will sample A minus 2 lambda, and I will come to 0. In each one of these lines, I will get minus a measure or plus a measure. And these measures, we know that they are i.i.d, because we already built it like that. So that's essentially what I'm trying to show in the drawing. You iterate. After you come back to 0, you iterate this construction. Because this construction has Lebesgue measure 0, but one can show that the small things that you are missing are really, really small. Okay, so that was my story about the Gaussian free field. And as I wanted to say somehow, at a point, like all of the stories just come out, at least the discrete stories, comes out of the metric GFF we have seen up to this point, and they have all been Markovian. However, now we can also get excursion decomposition of non-Markovian fields. And that this is fun. So which is our non-Markovian field we are interested in is XOR-Ising model. So what is XOR-Ising? Quite simple. You take two Isings, you multiply them. Okay. So I'm using plus minus 1 because you don't want to use 0. And then as you see, you get some funny shapes. So that was one Ising, that was the one we sampled for the Ising. For this product, it feels much more noisy, but still feels like you have interesting geometric behavior. So the first case I know that someone studied exactly the XOR-Ising was, so it's this paper of David Wilson, probably it was studied somewhere else before, but somehow he suggested that the level lines of this field were SLE4 type curves, which somehow is consistent with the bosonization story, and we are going to see that disappeared. Okay. However, the main difficulty of this field is that it does not have Markov property. Why? It's because if you have seen a part of the field, and then you want to guess the boundary, well, somehow knowing that how you change your spins gives you information about the law on the boundary of what you are getting. So the field itself is not Markovian. However, there is still a excursion decomposition for XOR-Ising. So on the discrete side, this comes out of the switching lemma. So essentially one works with a double current model, and the clusters of double current, they become the natural excursion decomposition in this side. What we proved with Tomás Alcalde recently is that this picture is converging, and I'm going to tell you to what it is converging. So why is this interesting? So in the continuum, so on the discrete it's clear that out of the shape of the cluster itself you can recover what were the values, because you can take values either plus 1 or minus 1, that's not surprising. However, in the continuum, then, so in the continuum, they will have conformal Minkowski content of a given dimension, which I put lambda and a and b here, so I haven't told you what's lambda. Lambda we know, it's pi divided by 2, but I haven't told you what are a and b, and they will come from the next idea. So where this comes from? So the main input is that the limit of XOR-Ising is equal to the sinus of the Gaussian free field or the cosinus of the Gaussian free field given the boundary conditions we have. How does one guess? Well, if I have free boundary condition, the field has to be big in the boundary. So it has to be something that's exploding, so it has to be a cosinus, because cosinus of 0 is 1. And if it's not, then it's the sinus. So here you get this 1 over square root 2. And so what can one show about this story? So both two things. So in this case, one cannot recover the excursions themselves out of the field. So this is clear in the discrete, but it has to be worked out in the continuum. That one has to build the same field that it has essentially two different supports. However, the measure itself is a function of the support. As we have said, it's just a conformal. It's just a conformal Minkowski content. So let me tell you. I'm going faster than I expected, so this is good. Let me tell you something about the proof of this, and this is going to be two of my most opal frames. But we will. Okay. No. So before that one. So let me tell you what do we use. So this is important. So now what we are interested in, we are going to generalize the question. So before the question was understanding XOR-Ising, but now my question will be to understand the excursion decomposition of the cosinus or the sinus of the Gaussian free field. And in fact, we are going to be concentrated in the sinus, because as you know, the cosinus has plus boundary condition. It doesn't have an exact excursion decomposition, because the cluster that is connected to the boundary is always positive. That's the only difference, and we will see it anyhow. However, we generalize the question. If I have put XOR-Ising, if I have put imaginary chaos, would have been less appealing than putting XOR-Ising, so I put XOR-Ising here. But the story is the following: you want to understand the cosinus of the GFF, but condition on. We want to understand the conditional law under one of the two-value set we studied before. Okay, and for this one needs a nice drawing. So the nice drawing is a circle. And I'm studying the cosinus, even though I said I wanted to study the sinus. So this is the following. Okay. So there is a certain value which is A critical, which corresponds to being. So A critical is just the distance between this and this. What do I mean by that? So you say that A critical times alpha, because I'm doing sines of alpha. I want them to be somehow living here. Let's imagine that A is equal to B. So I want them to be living in this side. As long as I am living in this part of the imaginary exponential, of the imaginary exponential of A or x belongs to minus AB. As long as the imaginary exponential of x times alpha remains in this path, then they are not providing any mass. Essentially, if one guesses what it should be the law, which is saying, okay, inside of each one of these connected components, I have the sinus of a Gaussian free field plus a constant, or the cosinus of the Gaussian free field plus a constant, then this happens. There is nothing magic, except at one point. So everything works well up to here, and then you get exactly 2 pi. Okay, so now you have your biggest enemy, and which happens to be your biggest friend. So it's like in anime. So I say, okay, everything was working well up to here. Yes. So when I was taking values here and here was working well, but then I hit it this part. Yes. And when I hit this part, there is something wrong that happens. So we are looking at the real part. So we are looking at the real part of the cosinus. And somehow we have to be in anything we build, because we are building conditional expectations. Yes, we have to keep the mean. So here the mean was 1 of the real part. Yes, and here I can boost. So this is going to be boosted. So the cosinus is boosted. So maybe I should have written it. The cosinus of the GFF, if you have never seen it, is just imaginary exponential of the GFF. The limit minus, so now it's plus epsilon plus alpha square divided by 2 log of 1 over h. So I am boosting it, because typically this is going to be going to 0, I have to boost it, and I have to do the same as in multiplicative chaos. Okay, and this is well defined for alpha between 0 and square root of 2. Okay. Okay, so now, if now I'm taking just 2 values, so what I wanted to say is, if I stop here, I'm just taking 2 values, but they are boosted, so the mean can be 1. However, when exactly you touch here, your real part is always 0. So this means that there is a problem. There has to be something appearing, because then if not, your mean would be 0. It doesn't matter by what you multiply 0. Yes, you could still get mean 0. So what happens here is that you have a measure appearing. Yes. So essentially, when you come all the way through here, now, okay, I have to erase something, or I have to do this. So,
Just
yes.
so that I can see point, there is a real part somewhere, right?
Yeah. Cosinus is the real part. Yes. It's either that one or imaginary exponential plus imaginary of minus exponential, which is how it's usually easier to get there. Okay. So essentially, the main idea is that we start with the circle. Yes, we have our two value sets. So here either I have cosinus of alpha a minus alpha a plus the GFF, or I have cosinus of alpha b plus the GFF. Okay, this works as long as I am still in the reasonable part of the circle. However, when this term is approaching pi divided by 2, the cosinus becomes a sinus. And what do I get? So this is how the proof is done exactly. So you take alpha rho to alpha critical, and you get in each one here, you get sinus. We already discussed the sinuses have 0 mean, so this cannot be the only thing that appears. And if one checks, what has to happen is that I have a measure appearing here. And this measure, one can show that it is equivalent to the conformal Minkowski content if the conformal Minkowski content exists. It's a really, if there is a conformal Minkowski content, it's that one. If not, it is a reasonable measure. That is a function of the field. So this is what we proved with Lucas and Frederick. One needs to show a little bit more for what we want, for every result we want. That's why I put Tomás and myself, because one also wants to show that this is exactly this equality. With Lucas, we have that the conditional law, the conditional expectation given what I'm seeing in A minus A is exactly that measure. And there is another interesting problem here, is that we are only able to do this exactly stopping at minus pi over 2, pi over 2. We cannot do a different type of thing, because in that case there should be, so the measure is not strictly a measure, so we don't know when it disappears and when it doesn't, and it becomes a problem for something that would naturally want to do. So now let me describe the excursion decomposition in the same drawing as I did before. So it's an awful drawing, so this is what I meant, and the next one will be was, but it is somehow an algorithm. Okay, so let me try to follow the algorithm on the board. Should I? Okay, I want to be a little bit German today. No, I'll keep this. I already said I should just. So you have time to look at the algorithm to see if you get it. And I'm going to be following it. So this is something that will not go for all alpha, it will go for alpha smaller than 1/2. Because alpha smaller than 1/2 will not put mass on CLE4. So again, as before, we want to use the signs of CLE4. Those are our only i.i.d. objects we want to have. However, there can be two cases. Either the CLE4 has mass, as in the result with Frederick and Lucas, or it doesn't have mass. And this depends on alpha, because the A critical depends on alpha. And this alpha, where it gives mass, is just 1/2. Big problem, we want 1 over square root 2. But let's see what one would naturally do in this context. So it's the following, so you start, so now I'm going to write it here on the disk, and I'm going to be following the algorithm. So I start here because I want to do the signs. Okay? So I start here well, here I said sinus, but and I either go to minus 2 lambda or 2 lambda. Because I know we are in the case where it is not giving me measure, I'm either going to minus 2 lambda here or here. So let's concentrate on the minus 2 lambda is here. So this is minus 2 lambda times alpha. This is the angle associated with plus I divided. So I'm here, and then here, now it's nice, I have a cosinus, okay? And a cosinus plus something, I can always come back to these points and get a mass. That's the trick. I always can come back to this point, I cannot come back to any other situation, but a cosinus plus something, I come back. So from this one, I will come back to either this one or this one. And this is what it is saying. At high minus 2 lambda, you either go to minus 2 AC, which is this one, if, well, it depends how to write AC, or you come back to this one. So if we did things correctly, this is what we want to do. And here you get a sign, a measure which was positive in this case. Yes, because I was here, if I would be here, you would get a negative measure. And then if you iterate this, and you stop at right times, then essentially you get excursions, which are given, when are the excursions? Excursions are exactly what I do when I do this step, and then you get signs. And who's giving you the signs? Well, the CL is giving me the signs, so I get independent signs. However, this is not what works for the XOR-Ising, which was our main motivation. So what does one do for XOR-Ising? And essentially one has to take a little bit of a more subtle approach, and it's really inspired by what it is done in the discrete. So there's this work of, so it's matching this, is Weikian and Dominic Copan, where essentially they show that certain observables of the double current model are converging to certain type of two-value sets. So when one looks at it, and one looks at their excursion decomposition, one gets that one has to do this thing. So it's a little bit more subtle, and surprisingly, it is not symmetric. One would want to take the CL4, but we cannot. Because now, the CL4 takes you here. We are crossing our allowed boundary. So one has to do something else. So we can go for alpha smaller than 1. What is the magic for alpha smaller than 1, and why we cannot go all the way to 1 over to square root 2, is that alpha smaller than 1 allows you to start giving mass to our smaller two-value sets. So the smaller two-value sets, which A minus lambda lambda, they have Minkowski dimension 3/2. They don't have Minkowski dimension 1. So then things would explode. So we need to start with a two-value set at least. And we do as follows. So we start with, so here I have to see. So I have to come to either, so I come to either AC, this is minus AC plus P divided by 2 times alpha. So I will go here and here. So here is, this is the simplest one, so I get here 2 lambda. So this is 2 lambda minus AC alpha and plus pi divided by 2, because I started in pi divided by 2. So I'm going either to that one side or to the other. And now one would say, okay, you are happy. You are now in this side. So why don't you make exactly a measure? Well, if I made a measure here, I would not get independent signs. Yes? Because I haven't still built the signs. These signs are really dependent. They are not at distance 2 lambda. I can never use distance 2 lambda. So I have to get the signs. So essentially what I have to go is I have to go to this minus alpha 2 lambda plus pi divided by 2, which is here. So I have to come here. I have to come to this value. So this is what I'm doing in the right hand side, and I am getting to it by a two-value set, because are the only ones that I am sure that they are not giving me mass. And if one is wise, I think that they are getting somewhere around here. I don't want to concentrate on those ones. Okay, but now I have ones of 2 lambda, and I would do the same one here. I would try to come again to this alpha 2 lambda alpha 2 lambda plus pi divided by 2. So I will get here also, but just using two-value sets. What is the great thing? So the great thing is that we know that at the point we arrive to 2 lambda, we arrive to a cluster, to a loop of CL4. So now we know that the sign here I may have arrived in a really weird way, but if I check condition on the geometry, the signs are i.i.d. And when I get to these points, I come back, and I get a measure. A measure with the sign given by the value of the sign of the cluster of the CL4. So then it has to be independent. So it's a little bit complicated, but thank you, that's all I wanted to tell you.